Derating is the reduction of a cable's current carrying capacity due to factors such as bundling, temperature, and length. The National Electrical Code, or NEC, requires derating for cables that are bundled together, as this can increase the temperature of the cables and reduce their ability to carry current safely. However, the specific requirements for derating vary depending on the type of cable and the conditions under which it is installed. In the case of 3M cable stackers, the manufacturer's instructions state that derating may apply. This means that derating is not always necessary, but it may be required in certain situations. Factors that may influence the need for derating include firstly, the number of cables being stacked. The more cables that are stacked together, the greater the potential for heat buildup and the need for derating. Secondly, the size of the cables. Larger cables have a higher current carrying capacity than smaller cables, so they may require less derating. Thirdly, the type of cable insulation. Some types of cable insulation are more resistant to heat than others, so they may require less derating. Fourthly, the ambient temperature. The higher the ambient temperature, the greater the need for derating. In general, it is good practice to consult with the manufacturer's instructions or a qualified electrician to determine if derating is necessary for a particular installation. In the case of 3M cable stackers listed for 814/2NN cables, it is likely that derating is not necessary in most cases. These stackers provide space between the cables and are not truly bundled, so they do not significantly increase the temperature of the cables. However, derating may be necessary in cases where firstly, a large number of cables are being stacked, which is more than 8. Secondly, the cables are exposed to high ambient temperatures. Thirdly, the cables are of a smaller size, for example, 12/2 nm. Fourthly, the cables are of a type that is not resistant to heat, for example, polyvinyl chloride or PVC insulation. If you are unsure whether derating is necessary for your particular installation, it is always best to consult with a qualified electrician. To further elaborate on the National Electrical Code, the NEC provides tables and guidelines for derating conductors based on various factors. These factors include the number of current carrying conductors in a raceway or cable, the ambient temperature, and the type of insulation used on the conductors. When conductors are bundled together, they generate heat. This heat can cause the insulation to degrade over time, which can lead to electrical failures and even fires. Derating the conductors reduces the amount of current they can carry, which in turn reduces the amount of heat they generate. The NEC provides tables that specify the percentage of ampacity that must be derated based on the number of current carrying conductors in a raceway or cable. For example, NEC Table 310.15. 8.3. Provides adjustment factors for more than 3 current carrying conductors in a raceway or cable. If there are 4 to 6 current carrying conductors, the ampacity of each conductor must be derated to 80% of its original value. If there are 7 to 9 current carrying conductors, the ampacity must be derated to 70%. The NEC also requires derating for conductors that are installed in high ambient temperature environments. The higher the ambient temperature, the lower the ampacity of the conductor. NEC Table 310.15. 8.2. Provides correction factors for ambient temperatures other than 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher than 30 degrees Celsius, the ampacity of the conductor must be derated. The amount of derating depends on the type of insulation used on the conductor and the ambient temperature. In addition to the NEC requirements, some manufacturers of electrical equipment may also have their own derating requirements. These requirements may be more stringent than the NEC requirements, and it is important to follow the manufacturer's instructions when installing electrical equipment. For example, when using 3M cable stackers, it's important to consider that the may apply statement implies a case-by-case evaluation. Even though the stackers are designed to provide space, certain conditions can negate this benefit. High ambient temperatures, particularly in enclosed spaces, can limit the heat dissipation. The type of insulation also plays a significant role. Thermoplastic high heat resistant nylon or THHN insulation, for instance, is rated for higher temperatures than standard polyvinyl chloride or PVC insulation. Therefore, cables with THHN insulation may require less derating compared to those with PVC insulation. Furthermore, the physical arrangement of the cables within the stacker can impact heat dissipation. If the cables are tightly packed, even with the stacker, airflow can be restricted, leading to increased heat buildup. In such cases, derating may be necessary, even if the number of cables is within the manufacturer's recommendation. When making derating calculations, it's essential to use the appropriate NEC tables and to consult with a qualified electrician if you're unsure about the correct procedure. It's also important to consider the specific application and the potential for future changes. For example, if you anticipate adding more cables to the stacker in the future, it's wise to derate the conductors accordingly to avoid overloading the circuit. Remember, derating is a safety measure designed to prevent overheating and electrical failures. By following the NEC guidelines and manufacturer's instructions, you can ensure that your electrical system is safe and reliable. When assessing the need for derating, several factors must be considered to ensure the safe and efficient operation of electrical systems. These factors include ambient temperature, conductor insulation type, number of current carrying conductors, and installation methods. Firstly, ambient temperature refers to the temperature of the environment in which the conductors are installed. Higher ambient temperatures reduce the heat dissipation capability of conductors, leading to increased conductor temperatures. The NEC provides correction factors in Table 310.15. V2. To adjust the ampacity of conductors based on ambient temperature. For example, if a conductor with a rated ampacity of 30 amps is installed in an ambient temperature of 40 degrees Celsius, a correction factor of 0.91 may be applied, resulting in a reduced ampacity of 27.3 amps. Secondly, conductor insulation type affects the maximum operating temperature of the conductor. Different insulation types have different temperature ratings. Common insulation types include THHN, XHHW, and THW, each with specific temperature ratings. For instance, THHN insulation is typically rated for 90 degrees Celsius in dry locations, while THW insulation is rated for 75 degrees Celsius. The NEC provides tables specifying the allowable ampacities for conductors based on their insulation type and temperature rating. It's crucial to select conductors with appropriate insulation types for the intended application to ensure safe operation. Thirdly, the number of current carrying conductors in a raceway or cable assembly influences the overall heat generated. When multiple conductors are bundled together, the heat from each conductor can raise the temperature of adjacent conductors, reducing their ampacity. The NEC requires ampacity adjustment factors to be applied when more than 3 current carrying conductors are present in a raceway or cable. Table 310.15. V3. Provides these adjustment factors. For example, if there are 7 to 9 current carrying conductors, the ampacity of each conductor must be derated to 70% of its original value. Fourthly, installation methods impact the heat dissipation capability of conductors. Different installation methods such as conduit, cable trays, and free air provide varying degrees of heat dissipation. Conductors installed in enclosed spaces, such as conduits, tend to have lower ampacities compared to conductors installed in free air due to reduced heat dissipation. The NEC provides tables specifying the allowable ampacities for conductors based on the installation method. It's important to select appropriate installation methods to ensure adequate heat dissipation and prevent overheating. To accurately determine the necessary derating, consider a practical example. Imagine a scenario where 612 American wire gauge or AWG THHN conductors are installed in a conduit with an ambient temperature of 35 degrees Celsius. The initial ampacity of a 12 AWG THHN conductor is 30 amps, as per NEC Table 310.16. However, adjustments are required due to the number of conductors and the ambient temperature. Firstly, the adjustment factor for 6 current carrying conductors is 0.8, as per NEC Table 310.15. V3. This reduces the ampacity to 24 amps. Secondly, the correction factor for an ambient temperature of 35 degrees Celsius is approximately 0.94, based on NEC Table 310.15. A2. Applying this correction factor further reduces the ampacity to 22.56 amps. Therefore, in this scenario, the derated ampacity of each 12 AWGTHHN conductor is 22.56 amps. This calculation ensures that the conductors operate within their safe temperature limits, preventing overheating and potential hazards. It is also important to consider voltage drop when sizing conductors, especially in long runs. Voltage drop occurs when the voltage at the load end of a circuit is lower than the voltage at the source due to the resistance of the conductors. Excessive voltage drop can cause equipment malfunction and reduce performance. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To minimize voltage drop, conductors with larger cross-sectional areas should be used. The NEC provides formulas and tables to calculate voltage drop based on conductor length, current, and resistance. When sizing conductors, it's important to consider both ampacity and voltage drop requirements to ensure safe and efficient operation. Furthermore, consider the impact of harmonic currents on conductor ampacity. Harmonic currents are non-sinusoidal currents that can cause overheating in conductors, transformers, and other electrical equipment. Nonlinear loads, such as electronic ballasts and variable frequency drives, generate harmonic currents. The NEC requires conductors that supply nonlinear loads to be sized to account for the increased heating caused by harmonic currents. In some cases, conductors may need to be oversized to prevent overheating. It's important to analyze the harmonic content of the load current and apply appropriate derating factors to ensure safe operation. Grounding and bonding are critical for electrical safety. Grounding provides a low impedance path for fault currents to return to the source, allowing overcurrent protective devices to quickly clear the fault. Bonding ensures that all metallic parts of the electrical system are at the same potential, reducing the risk of electric shock. The NEC provides detailed requirements for grounding and bonding, including conductor sizing, installation methods, and bonding techniques. Proper grounding and bonding are essential for protecting personnel and equipment from electrical hazards. Surge protection devices, or SPDs, protect electrical equipment from voltage surges caused by lightning, switching transients, and other disturbances. Voltage surges can damage sensitive electronic equipment and cause equipment failure. SPD diverts surge current to ground, limiting the voltage across protected equipment. The NEC requires SPD to be installed in certain locations, such as service entrances and at sensitive electronic equipment. It's important to select SPD with appropriate voltage and current ratings for the intended application. Regular inspection and maintenance are essential for ensuring the continued safety and reliability of electrical systems. Inspections should be performed periodically to identify potential hazards, such as damaged conductors, loose connections, and overloaded circuits. Maintenance activities such as tightening connections, replacing worn components, and testing protective devices should be performed to prevent equipment failure and ensure safe operation. A qualified electrician should perform inspections and maintenance to ensure compliance with the NEC and other applicable standards. Proper documentation of electrical systems is essential for troubleshooting and maintenance. The electrical drawings, panel schedules, and equipment manual should be kept up to date and readily accessible. Documentation should include conductor sizes, circuit ampacities, and overcurrent protection settings. Accurate documentation facilitates efficient troubleshooting and ensures that electrical systems are properly maintained. The selection and coordination of overcurrent protective devices, such as circuit breakers and fuses, are critical for protecting electrical systems from overloads and short circuits. Overcurrent protective devices should be sized to protect conductors and equipment from damage caused by excessive current. Coordination of overcurrent protective devices ensures that the device closest to the fault clears the fault, minimizing the extent of the outage. The NEC provides guidelines for selecting and coordinating overcurrent protective devices. Proper selection and coordination of overcurrent protective devices are essential for preventing electrical fires and equipment damage. Energy efficiency is an important consideration in modern electrical system design. Energy-efficient lighting, motors, and other equipment can significantly reduce energy consumption and operating costs. The NEC includes provisions for energy efficiency, such as requirements for lighting controls and high-efficiency motors. Implementing energy-efficient measures can not only reduce energy costs but also contribute to environmental sustainability. The use of arc fault circuit interrupters, or RFCs, is required in many areas of the home to protect against electrical fires caused by arc faults. Arc faults are dangerous electrical conditions that can occur when damaged or deteriorated wiring creates an unintended electrical path. RFCs detect arc faults and quickly interrupt the circuit, preventing a fire from starting. The NEC requires RFCs to be installed in bedrooms, living rooms, and other areas of the home where arc faults are more likely to occur. Ground fault circuit interrupters, or GFCIs, are required in wet locations, such as bathrooms, kitchens, and outdoor areas, to protect against electric shock. GFCIs detect ground faults, which occur when current leaks from the electrical system to ground. GFCIs quickly interrupt the circuit, preventing electric shock. The NEC requires GFCIs to be installed in all wet locations to protect personnel from electrical hazards. In summary, derating of electrical conductors is a critical aspect of electrical safety and system performance. The NEC provides detailed guidelines for derating conductors based on various factors, including ambient temperature, conductor insulation type, number of current carrying conductors, and installation methods. By following these guidelines and consulting with qualified electricians, you can ensure that your electrical systems are safe, reliable, and energy efficient. Understanding and applying these principles is paramount to maintaining safe electrical installations.